My name is Joe Soughayer, and I am the manager of business development at IonOptix. The MultiCell is our evolution of what we're best known for, which is our calcium and contractility system. So the calcium and contractility system allows you to interrogate excitation-contraction coupling in isolated ventricular myocytes, in iPSC-derived or induced pluripotent stem cell-derived cardiomyocytes, or any other immature cardiomyocyte. But it's limited in the amount of data that you can acquire in a given day, usually between 20 and 50 cells, depending on your experimental design. What the MultiCell does is it takes all of the high content data that you would get from our traditional calcium and contractility system, but it streamlines the data acquisition and analysis such that you can collect 100-fold more, depending on your experimental design, to get a much higher throughput. So instead of using an inverted microscope and the cells mounted on top of that microscope, and measuring from a cell, treating the cell, measuring it again in response to that treatment, and looking at things like the shortening and re-lengthening speed, or the amplitude of the shortening, or the calcium reuptake, or calcium release, what you would do is you would mark the position and measure from 100 or even more cells, and then treat the cells and go back to the exact same cells, so you have statistically paired data in a fraction of the time. So rather than make a measurement of a cell, then wash the cell away, put new cells in, and repeat, you would actually measure from 100 different cells at once. So how we've achieved this is, rather than bringing light in through the epifluorescence port of a standard inverted microscope, we've recreated that on our MultiCell microscope. And unlike the inverted microscope, where you have to manually move the stage, we actually drive the objective with fast motors, while the stage is fixed and stationary. This is important because if you were to move the stage really quickly, you would lose the position of the cells. The cells would actually physically move within the chamber. So by moving the objective really quickly, we can move from cell to cell to cell to cell without perturbing anything within the cell's chamber itself. We use red filtered light to interrogate the contrast of the cell. And this allows us to do one of several different algorithms. If it's adult primary cardiomyocytes, we can look at the sarcomere pattern, the repeating pattern of the sarcomeres, and run an FFT. So as the cell's shortening, we'll get a change in sarcomere length that we can measure in real time. And this is important because it's a quantitative indicator, and it's absolute. The cell's sarcomere length tends to be consistent from cell to cell. We can also, if we're looking at adult cardiomyocytes, we can look at the cell's length. We can measure the actual absolute length of the cell. If it's iPSCs, we have another algorithm called cytomotion that allows us to interrogate the contractility kinetics from those cells. So regardless of whatever the cell is, if you're doing calcium simultaneously, we bring in the epifluorescence illumination. Typically it's for calcium, so we have the cells loaded with FeR2. We bring in 340, 380 for its calcium bound and calcium free excitation maxima. And then the cells will emit at 510, and we split that 510 from the red filtered light that's used for contrast. That red filtered light will go to the camera. The 510 emission will go to a photo multiplier tube that collects the data at 1,000 hertz. So we can fully resolve calcium transients, and we can fully resolve on our fast CMOS camera the shortening dynamics of the cell. So typically, our customers are looking at characterizing excitation-contraction coupling, which is the work that cardiomyocytes do. Cells will receive a signal from external, depolarizes the membrane. Calcium comes in through L-type calcium channels, voltage-gated calcium channels, binds to ryanodine receptors on the sarcoplasmic reticulum. That triggers calcium-induced calcium release. That calcium binds to troponin C, and you get the mechanical action of the cell. And the whole process is reversed as calcium is taken back up into the sarcoplasmic reticulum through circopumps, or it gets pumped out through sodium-calcium exchange. So there are multiple processes within that our investigators, the customers that use our products, are looking to interrogate. They may make a genetic perturbation and they want to know how that genetic perturbation affects circuit activity. So they want to characterize calcium reuptake, and our data can be fit with our analysis with a single exponential function or a double exponential function, and they can look at how fast does calcium get cleared out of the cytosol and understand how their genetic perturbation might have affected circuit activity. Any process within that excitation contraction coupling can be interrogated with our systems. So the multicell, unlike our standard calcium contractility system, allows a much higher throughput. And what that means is you can ask questions and get answers much more quickly and much more statistically significantly. So if you're characterizing various compounds, for example, and you want to know how those compounds affect cardiac function, rather than having to drudge your way through weeks on weeks to get a single answer, all that information can be provided within a day's worth of experiments. Additionally, there are no other products on the market that offer high content data from adult cardiomyocytes, from iPSC-derived cardiomyocytes, with algorithms that are application specific for each of those model systems. And no other instruments on the market that allow for simultaneous quantitative calcium and quantitative kinetic analysis of contractility.